Добрый вечер всем. Доклад, я надеюсь, вы знаете, будет по-английски. Но я, как видите, понимаю по-русски более-менее. Так что если у вас вопросы, можете задавать по-русски. И в конце, если хотите что-то спросить или о чем-то говорить, тоже можно по-русски. Но доклады просто я читаю всегда по-английски, и если я попытаюсь рассказать вам про это по-русски, это будет очень медленно и долго. Ну и плюс можно английский практиковать немножко. So, hi everyone. My name is Sasha, and I don't know why you would know me, but maybe you've heard about me. But anyway, I will tell you about myself a little. I work for a company in Israel called Sela, and I'm the CTO, which means I kind of direct the technical operations at the company. We are a consulting and training firm, so we help customers with different kinds of things. We develop software for customers, so we don't have a product of our own. We build software for other people. We do consulting, so we help troubleshoot different kinds of problems, and this is part of my work as well. And we also do training, like talks like this one and longer courses as well. I personally started doing this kind of work, consulting, training, and development about 15 years ago. And performance specifically, which is the topic of today's conversation, performance specifically has been something I've been doing since the beginning. I started in C++ on Windows and Linux. We had this application running on both platforms. It wasn't Linux, sorry, it was IRIX, which is a Unix variant. And then I moved to .NET, and for the last 10 years or so, I've been doing mostly .NET on Windows, but also other languages and other operating systems, because I found that the performance process, building performant systems, investigating performance problems is more or less the same, no matter what platform, no matter what language. It's mostly the same process. And this is what I want to tell you about, the performance investigation process. And as a speaker, one of the things you're supposed to think about when preparing a presentation is what's in it for the students, what's in it for the listeners, like why would you hear this and be interested? And it's not that easy to answer that question, because I guess most of you are not already software developers, you're not writing software yet, you don't have your own system where you need to solve performance problems. And this is usually my audience. Usually I speak to people who need to go tomorrow to their job and use some of the things I talk about. So here it's a little trickier. And I think one of the things I would like to tell you about and for you to take out of this presentation is just that the real world is messy. And there's a lot of stuff that works and a lot of stuff that doesn't, and you should know about it. You should know what the process looks like in theory for building a system that will have good performance and for looking for places to improve performance, but you should also know how it works in the real world. So I guess this is something that could be interesting. If a lot of the things you learn are more theoretical, this could be more of a real world thing. So I have a couple of stories from my experience, and I also found a couple of places where I could make a connection to statistics, and so hopefully it might relate to some of the things you have been studying as well, maybe. So this is called the Performance Investigator's Field Guide, and so part of what I do is performance investigations, so I'm the performance investigator, let's suppose. And field guide because it's work done in the field. So you can't do performance investigations in front of an editor with a bunch of code in it. You actually go and talk to customers. You go and you talk to the operations people. You go and you try to look for little breadcrumbs that help you find the source of the problem. So it's really work done in the field. And I want to share with you, again, some of my stories, a strategy for doing that kind of stuff, for doing performance investigations. There are a few specific things that I would like you to learn, but anything you find interesting will be lovely for me. I really hope it will be interesting. And if you have any questions, you should know that in Israel, People are very rude and interrupt all the time. So if you have a question at any time, really just feel free to say. And if I need to speak more loudly or more clearly, then yeah, just tell me. So this is the general structure of a performance investigation. It's not, scientific theory. It's mostly things I found that work from my experience. So suppose someone is telling you they have issues with the performance of their system, their application, their computer, whatever it is, what the general steps are for trying and diagnose that kind of thing as a software person. This sounds obvious, but you need to understand what the problem is. You need to get a good description of the problem. And I will show you a couple of examples, but generally, people in the software world, they're not very good at communicating in general, and they are not very good at explaining what the problem is more specifically. So just understanding what they want from you is pretty hard a lot of times. So I will talk to you about some examples. The other thing that often helps me a lot as a person from the outside is to build a diagram of the system. And I mean, I know that when I was studying pretty much anything at university and later at work, it really helped me to have this picture of what all the different parts are and how they are connected. And even if it's something you already know, it helps a lot. But definitely, if it's a new system that you never saw before, just thinking about all the different components is really helpful. Once I have that, I usually try to run some kind of quick checklist to see what's happening in each of those components. Again, we're talking about software here and performance problems in software, but it's generally useful as a technique. You break the problem into pieces, and then you try to quickly look at each of the pieces and see if it's behaving the way it should. This is not a very extensive investigation. You don't spend days on it. You just want to get a quick understanding if all the different pieces are working correctly. And then hopefully that leads you to understanding which component is having the problem. And maybe some of this sounds completely obvious, but I'm telling you about this process and this structure because a lot of people just randomly fumble around when trying to solve problems. They use the random method. So they use something, and if it doesn't help, they move to the next thing. It's not a very good method. So this is why I point out some more specific things. So hopefully you understand at this point which component is having the problem. And this is when you spend most of your time, usually, doing a detailed performance investigation. And this is not a talk about the specific tools you would use. Because maybe tomorrow some of you will be building Java applications, and some of you will be building .NET applications, and some of you on Linux, and some of you on Mac OS, and some of you on Android. So I really can't give you tools which would work in each of these situations. But I can tell you that there are tools for all the different platforms, for all the different languages, and they look mostly the same, and they work mostly the same. So I know it's not very reassuring, but it is there, and it mostly works. So at this point is where you get the tools out, and you start really investigating the problem. And I will talk a little about tools, but not specific examples, just general principles. Hopefully, at that point, after investigating, you find the problem. You find the root cause. And by root cause here, I mean the thing that if you remove that thing, it really solves the problem. It's not just a symptom that you put a plaster on and it doesn't really solve anything. You want to find the underlying issue that you have to dig around for. And if you remove that, if you solve that, it really solves the problem for good. And it will not come back. If you really solve it, it will not come back. If you put a plaster on it, it will come back. So supposedly you found the root cause, and you fix the problem, you resolve the issue, and you make sure you really did. This is something a lot of people forget about it. They solve the problem, but then they don't go back and see that it actually helped over time and that everyone's happy now. So suppose we also figured out it solves the problem and we're happy and we're done. but we're not really done until we document the whole thing. And I know you probably get the chance to write a lot every day, a lot of different things. So, you know, documenting is probably not your favorite thing in life right now. And developers also don't like to write documents. I don't like to write documents. Nobody likes to write documents. But it's very important for your team, for you, for the future you 3 years from now, to document the whole process you have went through. And I know it's hard to imagine that you would need these steps you followed, you remember it all really well, but 3 years from now we will have a similar issue, and if you documented the previous one, it will be that much easier. And I found that good organizations, one of the things that makes them a good organization is the organizational knowledge they have. So it's not just a bunch of people, and this is a really smart guy, and he's really good at this. It's the organizational knowledge and documentation which makes the organization a bit bigger than just the knowledge of each individual person. And of course, I mean, if you find the job for someone better, and then someone else has to fill in your shoes and do the same thing, documentation is the only thing that would help them. So this is the general process, and the things I'll be talking to you will have to do with some of these steps. Again, it's not going to be like a recipe for solving all the problems. It's going to be examples and stories, mostly. So here's an example of problem description. And I haven't used like real customer names, but it's very close to the original text. It's not the name, but it's the text at least that's very close. So this is a typical performance report. The application feels slow. Users can't really tell you what feels slow, but it feels slow. Please solve the problem. Hopefully this looks a little ridiculous to everyone, because it's very not specific, right? Even if you know what the system is, even if you developed the system yourself, you still don't know what to do with this report. This is very typical. A lot of people just, that's the way they report issues. If you, by the way, encounter problems in products that you use, open source projects you might be using, development tools, the operating system you use, when you report problems, please don't be like that. Please be specific. Please explain what you were trying to do and how it differed from your expectations, what you actually got. Another example, which is more typical for consulting work like I do, we have a 2-day budget for performance work. Please come in and for 2 days sit down and look for problems. It's a good way to use a budget, and my manager doesn't mind. We're getting paid. But again, for an organization, it's not a good use of resources. You don't want to perform performance investigations or invest time in performance work just because you have the budget. You want to invest as little as possible in anything. That's just a basic principle, I think, of business. So this is also not very good. Here are a couple of examples which are a little better. They might look too detailed, but it's never too bad to have too many details in that line of work. So here's an example. Since 4:25 in the morning, there was a performance degradation where response time to my web application, which is written in ASP.NET, but it doesn't matter, response time has increased to 1400, sorry about that, to 1400 milliseconds, and it used to be 60 milliseconds. And that number you are seeing, 1400 instead of 60, it's not just any number. It says here this is the 95th percentile. If you're not sure what it is, we'll talk about percentiles a little later, but it basically means that 95% of my requests are faster than this number. So 95% of the requests are usually faster than 60 milliseconds, but now there was a degradation, and now they're only faster than 1400 milliseconds. A lot worse. And this is happening in all geographies. So maybe my system is available in China and in Russia and in the US. All over the world this has been happening. and it hasn't gone down, and there's some more details here. This is great because I know what to do. I also know when the customer will be happy. When time is going back to 60, they will be happy, because that's more or less their usual steady state. I know what they tried, because it says here a few things they tried. I know which system it is. This is like, I'm really happy when someone sends me something like this. I know it's going to be interesting. Another example, which is shorter but still useful. So suppose there is this medical application used by doctors and nurses in a hospital, and I get this email that says, in the latest beta version of that application, clicking from the patient details screen to the CT viewer screen takes 11 seconds in certain hospitals. Now, doctors and radiologists, they don't have 11 seconds to wait for a CT image to appear. They need to go through a CT image every 20 seconds. So I know this is bad, and it has to be under 2 seconds. Again, a very clear expectation, a very clear violation of expectations, and a very clear description of what's actually happening and what kind of system it is in general. I like these reports. This is a real story, and it was really fun to look at. Now, these numbers here, and what's acceptable and what's not, like how did we get to 2 seconds or 60 milliseconds, this is interesting in itself. And like, imagine for a moment you are building a system, and I'm going to ask you, what is a good response time for that system? How fast should it respond to user request? Or you're building a web page, and I will ask you, how fast should that web page load? It's hard to say. And so often, my conversation about this with customers is something like this. So I ask, what are your latency requirements? By latency, I mean response time, for example, or page load time, that kind of thing. And then they say, we need an average response time of 20 milliseconds. Now, it's pretty fast, right? You agree, I hope? 20 milliseconds is pretty fast. You can do a lot of things in 20 milliseconds, but it's still pretty fast. And so I usually ask, when they tell me something like this, is that the worst case? So can it be more than 20 milliseconds? Would something bad happen? And they usually don't really know. So maybe yes, maybe no. We didn't think about it. And then I go, OK, so some requests could take 5 minutes, and that would be OK. Because remember, an average is an average. And we'll talk about average a little later. But you can have an average of 20 milliseconds, and some requests take 5 minutes, right? An average can be anywhere, and your numbers, your distribution could be anywhere else. But of course not. It's like 5 minutes, it's ridiculous. Nothing can be worse than 100 milliseconds. This still looks suspicious, because even 100 milliseconds is very optimistic. If you build a real-world service without investing really a huge amount of money, it's hard to get to a worst case of 100 milliseconds for different kinds of things. So at this point, I might ask, even if it's just 2 requests per day, is it not OK for them to be slower than 100 milliseconds? So you see, I'm being annoying here. I'm being this annoying person who keeps asking questions. But I really want to understand the distribution, right? You get a sense here that I'm trying to get a distribution out of them, what the desired distribution is. And then they say the worst acceptable number should be 2 seconds. So we have a few bits of information here. Worst case has to be 2 seconds. Average has to be 20 milliseconds. That's what we know so far. So I keep being annoying. How often is a 500 millisecond response time acceptable? Because consider, you could have 96% of requests complete in 1 millisecond, super fast, and 4% complete in 500 milliseconds. And the average would be 21 milliseconds, because that's how averages work. And we have not violated the requirements here. It's hard, and it usually doesn't end very well. But yeah, thank you. Anyway, it usually doesn't end very well. But what I'm trying to say is there is a distribution in our brain. But you know, it's a little hard to put in a chat window, maybe. but there is some kind of distribution, maybe something like this. So 90% of requests have to complete under 200 milliseconds, 99% under 600 milliseconds, but all requests must complete under 2 seconds. Some kind of distribution like that really helps set goals for you, because you can't get a worst case of 20 milliseconds. And you can't just say an average of 20 milliseconds, because it doesn't say anything about the worst case. You have to find some steps along the way like this, maybe more than just these 3 steps. And people building big systems, like Google, for example, they have, for each of their services, a very well-defined distribution like this, a performance goal like this. Google actually have a really nice book which covers a lot of stuff about their engineering, called Site Reliability Engineering. I can put some links for you afterwards. But one of the interesting parts is where they talk about how to set those goals for their services. And one of the things they found is that if you make your services too reliable, if you don't talk about the worst cases, if you kind of just make people think that your worst case is close to your average case, people will start relying on you too much. And then when you actually have a slight performance problem, you will break a lot of other systems. So it's better to be clear about these things and don't promise too much. Even if you think you can right now deliver better, just give them the distribution. So obviously, all of this stuff, though, I don't know if it's obvious, probably not obvious. Not obviously, all of this stuff shouldn't like come from thin air. It should be based in reality in some way. And I mean, these numbers here are response times for a certain operation. But the question is this the operation that the user actually sees? Just as an example, think google.com or yandex.ru or whatever you prefer. You type in your query, and it goes to the server. And then at the server, there is some database. And that database has these performance characteristics, which is great, but it doesn't really affect you as a user directly. You as a user don't care about Yandex's database. You care about the time it takes to get stuff on your screen. You care about the relevancy of these results. You care about not having malware in your results. That's the sort of things you as users care about. So your performance metrics, it's pretty incredible. It took the software industry, I think, like 50 years to get there, but we finally understand that our performance metrics should come from these business characteristics and not from random numbers we just make up on the spot. So yeah, I know it's ridiculous, but it has taken the industry a lot of time to get there. So again, all of these things, they don't live in a vacuum. They should be derived from business goals. They should be derived from things your users actually care about. And actually the limits, they should also be tailored to what your users care about. You might be able to say, my service should have an average response time of 20 milliseconds, but it might be actually too aggressive. Like maybe the user doesn't need 20 milliseconds. For example, if you run a Yandex query and the page comes back to you in 20 milliseconds or in 30 milliseconds, you are not going to notice. And so maybe I can be a little more relaxed about my performance and put fewer people on it and fewer servers on it. This is also important, understanding what your user really needs. So a few observations like that. Let's sort of keep moving. I can sometimes just keep talking about things without moving forward, so I do have to move forward at some point. I want to talk about the investigation itself. So suppose we have these numbers and we know what we're monitoring. These are some of the mistakes a lot of people do when looking for a performance problem. I think it's actually more interesting than the right way to do things, because you can learn a lot from mistakes usually, even sometimes more than from some kind of process I will make up. So these are some of the common mistakes. The first is making assumptions. And it's probably true for anything in life. Making assumptions is bad, and you can really spend a lot of time chasing the wrong thing if you just assume for no reason the problem is in some place. I'll share with you an example in a moment. Trusting instincts is kind of similar, but it's not just assumptions. Some people think they have this, internal prophecy capability where they just know what the problem is, or they have this belief that something has to be a certain way. It's a little irrational, but it's a common mistake people make, especially under pressure, because imagine you're trying to solve a performance issue at 3 a.m. in the middle of the night. They woke you up, you're a consultant, you're really annoyed, and under pressure you could go with irrational beliefs pretty easily. So I'll have an example for you in a moment. Then we have look under the streetlight. There's this story, about the drunk person on the street, and then the drunk person is on the street, and a police officer comes around, and they see that the drunk man is looking for something under a streetlight. And the officer asks, "What are you looking for?" And he says, "I'm looking for my keys." So they go and look together, and the officer helps him, and they spend 10 minutes looking, and they can't find the keys. So the officer asks the guy, "Are you sure you lost them here?" And he says, "No, but the streetlight is here, so it's easier to look here." I've heard this, I think my mom told me this when I was like 7, it was her favorite joke. We do it all the time. We do it, your Internet Explorer or Chrome or whatever you use crashes, so you restart Windows and it helps. Or you can't save an attachment in a web browser. You assume it's too big. There's a bunch of these things we do when we assume, and we can similarly assume that the problem is somewhere where it's easy for us to look. And under the streetlight means, in this context, that if I have a tool that can show me exactly what's happening in some part of my system, I will spend all my resources looking there. It's really hard to get out of this mindset. Sometimes the only thing I do as a consultant is tell people, no, you should look here as well, and you should look there, and then eventually we just find it, and I don't do anything. I just tell them to look there. So that's pretty common. Then we have some tools-related mistakes. You'll find there are a lot of performance tools, like type into a browser Java performance tools or C# performance tools. There are a lot of them. Commercial tools, open source tools, free and commercial kind of mixed tools, stuff that the vendor provides like Microsoft or Oracle, and stuff that third-party companies provide. A lot of tools. And so a lot of people would use just every tool they can get from Google search results until something tells them what the problem is. Again, not a great idea, because some tools just really aren't related to the problem you're looking for. They can't help you with the specific thing you're facing. So no, running all the tools you can get access to is not a good approach for performance investigations. And, very important, blaming the tools is something a lot of engineers will do when desperate. You will just say something like, "This tool is lying, it's reporting the wrong numbers, I do not have 10 crashes every hour. This tool is wrong, my application is not using 20 gigabytes of memory, it's impossible." Or the other way around, the tool is causing the crash. If I didn't run this performance tool, everything was fine, but now you forced me to run this tool and nothing is working anymore. We tend to do that. We are trying to deflect into anything else, and so this happens very often. There's actually number 6 here, which I didn't put here. I didn't want to discourage you, but in a lot of organizations, number 6 is just pass the problem to someone else. Like, if you are the development team, you blame the networking team. If you're the networking team, you blame the infrastructure team. If you're the infrastructure team, you blame the development team. And you can keep going. Again, a good organization is where people are willing to take responsibility and investigate, and they will not say it's the networking team if they haven't done anything to establish that it is the networking team. There are very few places like that, and if you find a job at a place like that, stay there. It's very rare. Okay, so I want to tell you about a little specific example of a performance investigation which was not successful. So we don't know what the problem is until this day. So I'm that bad at my job. But the customer, well, I'll tell you about it and then you'll judge for yourself. So the problem was the following. There is this large organization in Israel which doesn't like using other people's software. So they will not use like common email solutions. They will write their own email solution. They will not use something like wiki. They will develop their own wiki and so on. And specifically, they developed their own document management system where one person can upload a document, another person can download it, maybe make comments. They built their own document management system, and surprisingly, they had some problems with it. The specific problem here I was asked to help with was load and save operations on documents would sometimes cause a timeout. So the user would try to load, and they'd get a window saying, you know, couldn't load, operation timed out. Same thing with save. The architecture of this thing, I have a very simplified diagram down here. The application of this, the architecture of this thing is we have clients running on their workstations, laptop, desktops, phones, whatever, and they connect to a central server, and that server is connected to a storage solution. Now, this was specifically a NetApp storage solution. NetApp is a company that specializes in very expensive storage solutions and very reliable and very everything. They're the big storage solution industry. And it's one of the problems with NetApp often is that it's like a black box. If you have a NetApp storage system in your company, you need a dedicated NetApp administrator. You need a person whose job is to take care of the storage. I don't know, they pet it in the morning, and I don't know what else they do, but you need a person dedicated to the NetApp storage solution. It's actually a problem because it means I just basically don't have access to that black box. I can see what the application is trying to do with that black box, but I don't know what's happening inside because they won't even let me touch it if I wanted to. There's a dedicated person for that. Just telling you about it so you can understand the process problems in here. Okay, so I wanted to see, because we had timeouts, right? I wanted to see if the storage was not causing the timeouts. I didn't blame anyone. I just wanted to make sure. So I wanted to investigate the storage latency, how long it takes to read and write stuff to that external storage system. Just to make it clear, it's a network storage system. So the storage system is one server and the application is another server. Okay, so this is going to be emails. I did 24 hours of processing, and I found on the network that the average latency to storage was 11 milliseconds. Averages are great, but then the worst case values I've seen were up to 1200 milliseconds. And this is more or less around where I would expect timeouts to start happening from what I knew about the system. So I was pretty convinced at this point that something might be wrong in that NetApp appliance, or maybe the network connection to that NetApp appliance. I had numbers. Okay, so I got back the following. Please find attached the network traces from the NetApp appliance. Again, just to clarify, we have the storage box itself, and we have the network cable or network in general going to that box. So at this point, they didn't look inside the box. They looked at the network connection to the box. And what they were able to say is the worst case network latency was 10 milliseconds. So in case you don't remember all the numbers, my worst case from the application server was 1200 milliseconds, so 1.2 seconds. They're saying the network part is just 10 milliseconds, which leaves 1190 milliseconds, which I think are inside the box, are inside the NetApp appliance. And I think it's not unreasonable to say that. Okay. Then they wrote the following. The NetApp consultant is not NetApp administrator, two different people. NetApp administrator is the one you pay all the time. The NetApp consultant is the one you need to pay extra when you have a really serious problem with NetApp. So this guy will be in next week. In the meantime, the administrator says that the NetApp storage latency is always under 5 microseconds. Very impressive. Like, wow, I wish I could build storage systems that have 5 microsecond storage latency. Then the consultant came the next week, and he said, no, it's actually 5 milliseconds, not 5 microseconds, come on. But it's almost the same thing. So in any case, the problem is not the storage. So you have your 1.2 seconds, I'm responsible for 5 milliseconds, you can go away now. I asked just one thing, is this the average or the worst case? I hope you understand why it's important, because I was working with worst cases. Is that an average or the worst case? Hold on, this is what they replied. It's the maximum average value over 60-second intervals. I don't think you need a lot of statistics to understand it's kind of weird to say that. What is the maximum average value? Do you take all the maximum values and then you do the average of them? Or maybe you take all the averages and you do a maximum of the averages. Not the same thing, right? Usually very far from one another. So we don't know until today what a maximum average value over 60-second intervals means, but this is just the number they were able to extract, apparently, from the storage system. This is what they said, anyway, that their storage system could report. I was surprised. So I tried, I used my Google abilities to search for, NetApp performance, statistics, monitoring. There are materials online on anything. And of course, NetApp monitoring is not as hard as, they try to make you think. The company obviously has an interest in the whole ecosystem where you need a NetApp consultant and you need a NetApp administrator. And the NetApp consultant, they come in with a backpack that says NetApp on the backpack. It's part of the, uniform, I guess. It's something you need to maintain, but there is actually documentation on NetApp performance monitoring. And I found that, there are some performance numbers that you can get out of any NetApp storage appliance. Here they are, and they include latency for reads and for writes, separately even for reads and for writes. And it's not the worst case, but it's at least the average every second, and not some weird number like the maximum average over 60-second intervals. Unfortunately, I think this kind of alienated the customer. So the fact I was, as a non-NetApp consultant, trying to explain that NetApp has certain monitoring features, and unfortunately there was no longer budget to bring the real NetApp consultant to investigate this, and we just stopped at this point. So we still do not know if the storage system was the problem. We still don't know what the latency to it was. And I mean, they didn't solve the whole issue. They still have timeouts. Well, maybe they fixed it already, but the last time I've heard, they still had timeouts. And what they did, remember I told you it would show a window saying operation timed out? They built a little utility which runs in the background on all the desktop computers at least, and clicks OK in that window. And then the system retries, and usually everything works. They didn't build something like that for mobile, though, so it still happens there. But for the desktops, they actually built that tool, and it solved their problem. So in a way, I guess maybe there is some optimistic part to all of this. Yeah. Anyways, yeah, let's keep going. So I've shown you a couple of examples of making assumptions and trusting irrational beliefs. I have examples of these things as well, but I think I'm going to skip them actually, because I do want to talk to you a little about the right way maybe of doing things, like how to methodically approach a system with a lot of components and try to understand what's responsible for the performance problem. So there is a very smart person whose name is Brendan Gregg. He used to work at Sun, where he worked on Java performance, and then he went to work for Joyent, where he worked on Node.js performance, and then he went to work for Netflix, and he works on Netflix performance. So today, he's responsible for a lot of the Netflix performance architecture. And Netflix have a pretty impressive performance in their stack. So he came up with this approach called USE, which is a quick way of identifying which resource in your system might be responsible for the problem. It's very simple. USE stands for utilization, saturation, and errors. I'll explain in a moment. And his approach says, build a diagram of the system, which I always also recommend. And then for each component, find these three things, utilization, saturation, and errors, and work on resolving them individually. Now, what is utilization? Utilization is a metric of load. So, for example, you can express utilization as the proportion of time a resource is working as opposed to being idle and not working. So, for example, in a CPU, the utilization is the proportion of time the CPU is executing instructions as opposed to just sitting there being idle. For a memory system, you could look at utilization as capacity. So for a memory system, if you have 24 gigabytes of memory, maybe you can say utilization is the amount of available memory. But maybe you could also say this 24 gigabyte memory system, the maximum I can read per second is 5 gigabytes. So you could say utilization is how much I read compared to how much I could read at the best case. So there's different ways of defining these things. But utilization is a metric of load. Then we have saturation. Saturation is a metric of overload, of queuing. Do you have a resource where you can't service all the requests and you have a queue, so some requests are actually waiting to be serviced? Examples. For a CPU, you might have more things to do on your system than you have CPUs to actually do. So if you have 10 things to do and 2 CPUs, then 8 things are going to sit there and wait for a CPU to become available. So this is a good metric of saturation for a CPU, the number of tasks waiting for that CPU to become available. For a network interface, for a network card, you could look at saturation as packet loss. So if the system isn't able to receive any more packets because it's 100% busy processing packets, you have packet loss, packets are getting dropped, and that's also a metric of saturation for something else. And finally, errors are just errors. I mean, you know what errors are. And for different resources, errors mean a different thing. So for a memory system, if your memory in the computer has an error, it's pretty serious, but it happens. Most of the consumer-grade memory you buy will eventually have a memory error. Sometimes you can recover, sometimes you need to restart your computer. Disks, of course, also sometimes have errors. Network has errors all the time. So a network card getting some data which isn't in the right format or that you have to drop is completely standard. So you can look at errors for various kinds of resources as well. 3 simple things. And for each resource, for each component in your system, you want to look at utilization and see if it's too high or too low for your expectations. You want to look at saturation, and saturation is usually bad, so you don't want to have saturation. And of course, you want to look at errors, and naturally, you don't want to have any errors unless you must. And it's, again, so simple sometimes to look at it, but it's very effective to just organize things like this in your mind. So here's an example of a hardware system. So this is like a super simple computer which has a CPU, and the CPU, you know, these days most CPUs have multiple cores, so actually multiple CPUs inside a single box. And then you have the memory controller, which navigates memory accesses to the memory system, to physical memory. And you might also have a graphics card, and you might also have an I/O controller, and you have a disk connected to it, and a network card connected to it. I'm not trying to say this is what all computers look like, but a fairly typical representation. So here's why I show you this. First of all, for each of these resources, of course, CPU, memory, disk, and so on, you could look at utilization, saturation, and errors. But the connections are also important. The buses or connections that drive data from side to side are also important to look at, because surprisingly, they can also be bottlenecks. And unless you have this methodology, you can miss them completely. Just a tiny example, if you do any kind of algorithm optimization, usually what you try to do is optimize things inside the CPU. You want to do less work, right? You want to perform fewer instructions because it's going to be faster. You want to use a better set of instructions, that kind of thing. But this connection here to memory is actually quite as important, because if you optimize really, really hard, at some point you can get to a situation where the CPU is basically not able to read from memory or write to memory fast enough for your amazing algorithm to work anymore. And then you can keep optimizing the algorithm. You can keep finding breakthrough ways to eliminate even more work, but it's not going to help you because you can't read or write from memory fast enough. And so this connection here, the front side bus, is actually often a bottleneck in modern systems, because we have more and more CPUs sometimes and only a single piece of memory, and they are all trying to get to it, and it's really easy to saturate that resource. This is hardware. Same thing works with software as well. So this is like an architecture diagram for a simple web application. So I have here multiple web servers. I have on top of them some kind of router or load balancer. I have some additional applications running, and I have a database at the bottom. The actual products, of course, are not important, but you can draw a diagram like this for any system you build or for any system you built. And for each software resource, you could also look at utilization, saturation, and errors. So for example, for your web application, you could look at the number of failed requests or the exceptions per second as a metric of errors. For your front-end load balancer or router, you could look at requests per second being processed as a metric of utilization. And here you should also look at the connections between these things, because often in software we have, again, along these connections, some kind of bottleneck which can slow things down. So really, a method that works surprisingly well is just to get this kind of picture of what resources you have, hardware and software, and try to map utilization, saturation, and errors for each of them, and then just kind of go ahead and solve all the problems you see along the way. It also helps to not focus on components where you know there isn't a performance problem. Now, I don't know if it's actually going to be helpful or not, but I have a couple of slides. I'll share all the slides with you. But I have a couple of slides here just showing examples of how to get these metrics, for example, on a Windows system. I put it here just as an example, just to illustrate it's easy and it's not something you really should spend more than a couple of hours on in a real system to be able to capture these metrics. So if people tell you it's hard to measure exactly the utilization of a network card, it's usually bullshit, and you can usually pretty easily get this information from the operating system or from some other monitoring tool. And again, this very basic level of investigation usually doesn't really take a lot of work. And for all of these things I put here, there are, of course, automatic tools which can monitor these things, which can record these things. Again, I'm just giving these as examples. If you're not on Windows, Linux has, of course, a set of tools like this. Mac OS has a set of tools like this. Like I told you in the beginning, after doing performance work for a while, I really understood it's all the same. It's just, you know, here you need to use a tool called blah, and here you need to use a tool called foo, but it's really all the same. So I want to talk to you about another short story, and then we'll talk about statistics a bit and wrap this up. So the short story I want to tell you here is how we found a bug in someone else's software. So, you know, there's me, there's the customer, and then there's actually someone else whose fault it was this time. So I don't know if you're using C# and .NET or if you learn it at any point, but it has some popularity, obviously. And back in 2008 or 2009, I was investigating this really annoying performance problem that had to do eventually with a bug in Microsoft's implementation of .NET itself. And by the way, if this is also something you can take from this talk, it's usually absolutely counterproductive to assume that the problem is the compiler, the problem is the operating system, the problem is the browser. It's usually your problem and not the operating system. But sometimes it really is. So it happens, and it's also important to keep in mind that Microsoft engineers and Google engineers and Yandex engineers and Facebook engineers, they are just people and they make a lot of mistakes. And there's nothing that makes them these magical gods who never make bugs. So yeah, looking at the specific case, we had a system which was basically connected to this large network router. It would receive a huge amount of traffic, and it needed to make very simple decisions. Basically, more or less record certain packets and let certain packets just keep going. It needed very, very basic inspection of the actual data. It mostly needed to look at the beginning of the packet, at the header, make a quick decision, and keep going. So that's the system. And in that system, it was pretty important to do the whole thing fast. So from the moment the packet goes in, we had sort of a deadline. We couldn't spend like 5 minutes looking at the packet. We had to get it going pretty fast. I'm saying just pretty fast because it wasn't like a critical system like what you put in a hospital or what you put on a rocket, right? It's not that kind of mission critical stuff. But let's say if the whole thing was slow, a lot of things would fail later on. So what we saw is that occasionally this kind of critical system was missing lots of packets. So lots of the data coming in would just be dropped. And we had logs. Back in 2008, even having some log messages printed by the application was impressive. I'm kidding, but it really, really had good logs, very detailed logs. And one of the things the log showed is here, I'm starting to process a packet, and the timestamp is 44 seconds, 057 milliseconds. And then 500 milliseconds later, I'm saying I finished processing the packet. So that, I mean, we thought it proves that there is a bug. We have some kind of delay in the code. We need to optimize it or something. But we looked at the code, and there was nothing to optimize there. There was no way we could actually make it take 500 milliseconds. We tested it from all different sides. It was never running for more than maybe a millisecond. No way we could reproduce this in our environment. Another little lesson from this, some bugs are of course very simple, and you run it in your debugger or on your machine, and you just see what's wrong. But some issues, you just can't even make them happen in your environment. And then you have to, you know, diagnose in the field, like where the issue is actually happening. And this was a thing we thought would be easy because it's just, you know, a simple algorithm, looks at the packet, decides what to do, but we couldn't make it as slow as it was in the actual environment. So we got working on some metrics, and we got this beautiful graph. It's not the real one. I simulated it later in MATLAB. But this is two metrics here. So the red is CPU usage, and the blue is, sorry, the other way around. The red, yes, the red is CPU usage, and the blue is number of packets being processed. And you can see this is the timeline here, time in milliseconds. Everything is going just fine. CPU usage around 40%. Packets being processed really nicely. And then obviously something happens. There's a cliff, the whole thing drops. And it drops in two stages, which is interesting. It first drops where the CPU usage goes to like 20% instead of 40%. But the packet processing goes almost to zero. Not completely zero, but very close. So it's still doing something, but very slowly. And then there's this little period here, which I don't know if everyone can see, but there's this little line here, 0 packets, nothing happening, but CPU at 100%. This is what we saw. And it was happening like every few hours. Not all the time, so it was lucky enough for us to catch this thing. And here's another funny observation. The delays, these windows of delay, were always close to a multiple of 250 milliseconds. And this is like voodoo territory. So it's not just randomly stopping. It's stopping for 250 milliseconds. Or 501 milliseconds, 752 milliseconds, that kind of numbers. There has to be, like somewhere, someone must have written 250 in the code. It has to be there, because otherwise there's no way to explain these weird numbers. So I don't know if it's something that comes into mind, but whenever there is this kind of delay in a system that's using garbage collection, like Java and Python and .NET, one of the things that should come into your mind is whenever you have those delays in a system with garbage collection, it could be the garbage collector. The garbage collector has this way of stopping applications, doing the garbage collection work, and then resuming the application. It exists in more or less all the languages using garbage collection. So again, Java, Python, Node.js, JavaScript, that is, C#, of course. And I suspected it had to do with the garbage collector because we had those delays, but the 250 milliseconds we didn't really have a way of understanding. So it took us a lot more time to get there, but we were able to get a picture of what the application was doing during one of these delays, during the part where some packets are still being processed. And so I'll make the story a little shorter. What we discovered was, yes, it is related to the garbage collector. The garbage collector wants to start garbage collecting. It wants to start cleaning memory. But it can't, because in order to start, it has to stop the application. So it hasn't stopped it yet. It's just trying to. But the application is not cooperating. So the garbage collector is trying really hard to stop the application, and the application doesn't want to stop. And the garbage collector keeps trying, and the application keeps not stopping. And then again, I'm going to cut the story a little short. We actually found code in the garbage collector's implementation which had a 250 millisecond delay. So at least we were able to understand where the multiples are coming from. So basically what we found inside the garbage collector was a piece of code that said something like, I want to stop the application. let's wait for 250 milliseconds and see if the application has stopped. If not, let's try again. And sometimes it would succeed after one time, sometimes after two, sometimes after three, sometimes even after 5. So we had delays all the way up to 1.25 seconds. But we were almost sure this is the code that had to do with it. But going back to 2008, the .NET garbage collector was not open source, like go ahead, read the code, fix the bug, use it now. It was a proprietary Microsoft product. And so this wasn't really code, it was assembly really. But we discovered what we thought was a bug. And I didn't have a lot to do with it. So I wrote a blog post on my blog. I don't blog much these days, but once I used to write like 50 blogs a year, 50 posts a year on different technical issues. And I just documented what I found, and I said, you know, maybe someone has an idea. The first comment I got was a person from the UK who had the same problem. And they basically got to my blog by looking for 250 milliseconds on Google. So they found me. And then we had the bug together, and we were happy. But eventually, I think it was maybe 3 months later, I got a response from Maoni Stephens, who was at the time the lead developer of the garbage collector at Microsoft. And she just found it randomly, probably online. And she said, yeah, I ran your example, and I can see the problem. We'll have someone take a look at it. And it was actually a bug in the garbage collector itself. And so a little while after this comment, we got a hotfix, which is a private version with a fix. We tested it, it worked. We told Microsoft it worked, and there was a happy ending to this whole thing. It was also an example, in addition to like the happy ending, it's also an example of how much harder things are when you don't have the source code for a product. This is one of the things it took me a while to understand, but this is one of the real appeals of open source, that if you're willing to invest the resources, eventually you can understand the source. And it's not like the Linux kernel or the Java sources are very easy to read. They're not. But if you invest enough resources, you have access to the source code and you can understand the product completely. With a closed source product, you can't. You can invest as many resources as you want, but there are still things you will not understand. And again, the code I showed you here was not actual code, it was disassembly, and it was just a tiny piece which I happened to find by accident. But generally, this kind of investigation could have taken months and still not really result in any useful output if in a closed source product. And I know it's funny that I'm here and I'm a Microsoft person and I'm working on Windows and .NET and all that, and I'm telling you open source is good. But even Microsoft kind of realized that. And so .NET, for example, today is open source, and the C# compiler today is open source. Probably the only thing of the whole story here that's not open source yet is Windows itself. But I hope we'll get there as well. So again, for me, one of the appeals of open source is getting to the bottom of any problem you have eventually. So I want to talk a little now. I think I'm going to skip a bit. I want to talk just about one more thing to not bore you to death. I want to talk a little about statistics. Some of the things I talked about today were averages and worst cases and that kind of thing. And of course, you understand all of it. But a lot of people in the software industry, they have this really strong belief that averages are the only thing you should care about. If you monitor performance, you should have a big screen which shows a lot of averages. This is how you monitor performance. It has the average response time, the average CPU usage, the average memory usage. This is what you need to monitor performance. Unfortunately, averages are almost meaningless in the real world because in many cases, your distribution is very far from the average. and you have weird distributions, which aren't, you know, uniform or normal or exponential or any other distribution you study. One other thing is medians are almost as meaningless for the same reason. So the median value could be maybe a little more representative in some cases, but still without seeing the whole distribution, in a lot of cases it's still meaningless. Percentiles, which I mentioned, and we'll come back to them in a moment, are a little better. But the best thing I found, and a lot of people are starting also to agree, is just seeing the shape of the actual data. So it's really hard to bring a lot of data points down to a single number. Don't even try. Just show me the actual numbers. Just show me the original shape of the data. And one other thing I want to talk about unrelated to this is coordinated emission, which I'll get to. So first of all, averages. The average response time is 29 milliseconds. And that's on your big screen. Sounds good, but really doesn't mean anything. So this distribution has an average of 29 milliseconds. This is a histogram, right? So this histogram has an average of 29 milliseconds. And in this histogram, most values are clustered around the average. I generated this histogram using a normal distribution, so of course most values are pretty close to the average. The worst case here is like 60. So the average is 29, the worst case is 60, users are happy. But this distribution also has an average of 29 milliseconds. The average, in case you can't see it here, here's the average. This blue line here is the average. Most of the data is on the left side of the average, but I have this cluster here, which is at 200. And that's not really close to the average. And in fact, there are no values at all, I think, which are really at the average. I have stuff a lot less or wildly more. And this is very typical in performance monitoring, where you see this weird distribution. One way of characterizing it is it has multiple modes or multiple clusters of data, right? And just if you think about it for a moment, why would this happen in real data? Many reasons. For example, these could be users from Yekaterinburg. These could be users from Israel trying to access a server which is here. Perfectly reasonable to have this kind of distribution, just because of the network speed. Or this could be file accesses to the disk. And you probably know file systems and operating systems, they have a cache in memory of files that you recently accessed. So this could be files you recently accessed, and so you can read them from memory really fast. And these could be files you actually have to go to disk and read from disk. And the disk is like 10 times, actually even more, slower than main memory. So this is not like random numbers Sasha made up. This happens all the time. Like probably most data in computer performance is more like this than like this. Which is, again, why averages are really hard to make any sense of. Now, there is a tiny piece of research I wanted to share with you. Well, hard to call it research, it's an article by Autodesk, by a couple of guys from Autodesk. All the different clusters of data you see here have the same average across the x-axis and the x-axis and the y-axis. They also have the same standard deviation, and the x's and the y's even have the same cross-correlation in all of these pictures, including the dinosaur. So this hopefully also explains why averages are kind of meaningless if you don't see the actual shape of the data. And a lot of people really trust averages way too much. Now, I want to share another example from averages. This output here, there's a lot of text, you don't need to read it all. This output here is from a really great tool written by Andrea Kinchin. You might have heard of him. He works at JetBrains now. He's a PhD in statistics and computer science. He knows this stuff, like he understands statistics. And he wrote a tool called benchmark.net, which can be used as follows. You give it a little piece of code, it runs it many times, and it tells you how fast it is. That's what it does. And they spent a lot of time working on this project. It's really popular, it's open source. Microsoft employees are using it to measure performance. It's amazing. And the output, if you can see it from behind, has a lot of stuff. I'm not even sure what it is, like kurtosis. So apparently it's some way of looking at data and saying things about it. So kurtosis. Skewness is probably also means something. There are things I understand, like average, standard error, standard deviation, minimum, median, the first quartile, so the first 25%. These things I understand. What is kurtosis, I still don't know, but never mind. Point is, the shape isn't here. I can't see the shape. Even if you print 5 more numbers, I still can't see the shape. And you know why Andrei doesn't print the shape? Because it's hard to print to the terminal a picture, right? So he just does that. And if you have additional software installed, he will generate a histogram and put it in a file. But most people don't have the extra software, and most people won't even know there is a file. So he knows it's important, and still, like by default, this guy who has a PhD in this stuff prints just numbers. I'm saying it completely as a friend. We talked about this many times. It's a hard problem. But I'm saying this is software designed to show you performance of a particular piece of code, designed with a lot of statistical features in mind, and it still doesn't show you the shape of the data. So it's something really that we as an industry are in desperate need to improve. One other example, and it shouldn't look like I'm picking on benchmark.net because it's really a great product, but another example from benchmark.net. It prints the number of times it ran your code, 52. But then if you look closely, it says down here, you can't see it. It's like gray on black, and it looks the same when you run it. It's invisible. It says 11 outliers were removed. 11 outliers were removed. Outliers are values which aren't close to the average. So he basically took the most interesting things and removed them. Why? So we can get a more consistent result, which you can compare with other results. So, the weird results are thrown away so they don't kind of hurt your perception of the world. It sometimes makes sense, but even in a benchmarking tool, it's debatable. But please don't do that in like real performance work. You are not allowed to throw away results because they don't fit whatever theory you have in your mind. It doesn't work like that in general. So here, for example, is a very typical picture of response times from a web application or some kind of web system. This is what it looks like. Most values are just, down there, perfectly legit. And if you look at percentiles, the median is here. The 90th percentile is here. So 9 out of 10 are less than this. The 99th percentile is here. So 99% is just clustered in this region. But then, outliers, 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 outliers. I call them hiccups in this picture. And the thing about performance work is the hiccups are what you're being paid for. Because, the average is nice, and the median is nice, and even the 90th percentile is nice. But literally, sometimes you are being paid for solving the hiccups. So for solving the worst cases, for solving maybe, well, not the worst case, but the 99.99th percentile. So if you look at this data, I've put some numbers on there. The average is 35, the standard deviation is 50, and you know, if this was a normal distribution, then looking at the mean plus 3 standard deviation is usually what they say all the values are in, or very likely all the values are in the mean plus minus 3 standard deviations. Well, here, the mean plus 3 standard deviations is just 188. And I have values all the way to 1,000. So it's just, you know, stuff isn't normal, and hiccups happen, and these are the things you should be investigating. And I'll tell you in a moment why the hiccups are what you should be investigating. One final thing about this, sometimes this kind of diagram is a little too messy. So there's an alternative visualization which works really well. You should know about it. It's useful for presenting results in general. And it's called a cumulative distribution or a percentile chart. What we're doing here is just putting the percentage points on one axis and the value we get on the other axis. So for example, the way you read this is, so 0.8 here means 80% of the values are smaller than this, so 50 something. 90% of the values are smaller than this, so 100 maybe, and so on. So you can see the shape of the distribution in just one simple chart. It's sometimes really helpful, and it shows you the asymptotic behavior also. This is an alternative version, more or less the same. It just shows you can put multiple together. So you can compare versions of your implementation by their distribution. Not just by the average, not just by the kurtosis, but by the whole distribution. And then you can say, this is better for all the values, this is better for the worst case, this is better for the tail, this is better for the head, and so on. So these are just visualizations, but a lot of people in software just focus on averages so much. Yeah, so just one more thing about percentiles I wanted to show you here. Like, who cares about percentiles which are so close to the worst case? Like, who cares about the 99th percentile or the 99.99th percentile? So if you have users in Ekaterinburg, they should get good results. Who cares about the one user from I don't know where who's sometimes getting a bad response time? Thing is, sometimes these things are interrelated and tend to add up. So I went to Amazon.com in a browser, and it was trying to advertise a bunch of stuff to me, of course. But what's interesting, I looked at all the requests it made. And going to Amazon.com produced 328 requests to Amazon's server. Now, if you haven't seen something like this before, it's actually not that unusual, because think about it. You have the web page itself, sure, but you have images, you have scripts, you have style sheets, you have a lot of dynamic content in here, which is being loaded after the page arrives. So loading Amazon.com makes 328 round trips to Amazon. Now, what is the probability that I will see a 99th percentile request, or worse, if I make 328 requests? It's not really 1% anymore. It's really 96%. Again, under a lot of assumptions, like all the requests are independent, I have the same likelihood of getting the 99th percentile, but now that I make 328 requests, there is a 96% chance, one of them at least, will be in the 1% of worst requests, which more or less means I will always see one of these worst cases. And to make it even worse, some of these might actually depend on each other. So I can't start the 325th one without completing the 324th one. So if the 324th one was slow, it also slows down all the other ones. So this is really an optimistic assumption. So in reality, all the users are going to see a lot of bad requests. And if you just look at the nice screen you have, and you see the average, and you're happy because that's what the average user is seeing, it is not what the average user is seeing. Yeah, so I try to sort of keep this within reasonable time bounds. So there's really just one final thing about statistics I want to talk to you about very, very shortly, and that's called coordinated omission. It's a very common problem when looking at performance. It's so intuitive, but it's so wrong. So here's what it is. Just skip to the actual result. So suppose this is what you have when you look at your system. Over time, for 100 seconds, you had 10,000 requests, and each request took 1 millisecond. Awesome, super fast, 100 milliseconds of running time, 1 millisecond, 10,000 requests, 1 millisecond each, you're doing really well. And then there's something really bad that happens, like maybe a garbage collection, or maybe something else that stops you completely for 100 seconds. And then everything goes back to normal, and you keep processing requests, and each request takes you only 1 millisecond. Where's the problem? The problem is how you measure averages in this situation. A lot of tools, what they will do, they would sit on the server, and they would look at the time it took the server to process that request from start to finish. Now, the request that finished here in 1 millisecond, it could have started here. Didn't get it yet. It was sitting on the way to the server somewhere because the server was busy with this one slow request. And so we could miss completely all the waiting time. It's very common, unfortunately, when measuring response times to ignore the waiting time. You only look at how long it takes you to do the work, but you forget about the wait time that the poor person had to stand in the snow waiting for you to service them. And so this could really change the numbers, of course. If you look at the first alternative, where you're only measuring the actual processing time without the waiting time, then you get an average of 11 milliseconds across this whole data set, and your 99.99th percentile is still 1 millisecond, because you only had this one really bad request. But if you consider that during this period, there were a lot of requests queuing up at the same rate as before, then actually the requests that were queuing up here had to wait anywhere from 1 millisecond if they got here, or 100 milliseconds if they started waiting here. And then your average doesn't look so good. The average for these requests here is actually 50 seconds, and of course your 99.99th percentile is 100 seconds. I'm only saying this because it's really a common mistake to make. You only look at the time it takes you to do the work, because that's what you're put in your work log, but you forget about the poor person standing in the snow waiting for you to service their request. In a lot of systems, there is no queuing because the system is always available and always ready to receive requests, but then suddenly something happens and you have requests standing in line, and that really screws up your numbers, but you don't know because you're not measuring the queue time. And this is called coordinated omission. It's a really common mistake in performance monitoring. And again, I hope it's natural from the statistical point of view that looking at just the response time, the processing time, does not represent the real experience for whoever is making these requests. So just a few examples and stories I want to share with you. To wrap up, I wanted to focus for a moment on the last thing on my list of steps in a performance investigation, which was the post-mortem, the documentation. Like, what do you come out with after spending weeks of your life on a problem? And very often, what you want to come out with is like plane tickets to a warmer place and just take a vacation. But what you really should do before the vacation is document the whole process. And just a couple of things to think about. What was the process you followed? Was it good? Is it a good fit for your organization or not? Which tools did I use? Did they work for me? Did they not? Was it worthwhile buying these tools and paying $100,000 for one license of one tool on one computer? Did it help us really enough for that? What other teams could benefit from the same process? Maybe I should share this documentation with them. Maybe it's just the future me. Maybe it's other people on the team or other teams who could benefit from this information. How can you make it simpler for people in the future to solve the same problem? For administrators to detect it, for users to be able to self-diagnose and solve it, for developers to be able to find the root cause and fix it sooner, so that sort of thing. And finally, one thing to think about for the future, maybe we could just solve the whole thing automatically next time. Like, find the problem automatically, find the root cause automatically, fix it automatically, make sure it works automatically, and just not involve any humans in the process. And again, the really successful players in our industry, which are scaling to millions of servers and who have hundreds of millions of users, one of the key things that helps them get there is automation. Because you can't put engineers on every problem again and again and again. Anything that a computer can do, a computer absolutely should do. And so we know today to program a computer to do a certain task, a program. We even know today how to make a computer verify that a solution to the problem actually solves the problem. But we absolutely should and could have ways to have computers diagnose themselves and fix themselves, heal themselves, and there's a lot of research and work on self-healing networks, self-healing systems, and again, the big players are all adopting this because that's what gives them the edge. That's what helps a company like Yandex have, say, 10,000 engineers, but 10 million servers, which really doesn't scale if you had an engineer responsible for each server. So just a few things to think about, again, in terms of the future for this whole area. I hope a lot of performance investigations would be a lot more automatic in the future. So we talked a little about what a performance investigation looks like. I shared with you not specific tools, but at least some stories and examples, which hopefully give you an idea of what my job is like. We talked about statistics, and I hope it sort of rings a bell, these concepts we talked about, and how easy it is to mislead yourself by looking at the wrong numbers, essentially. There are some links here if you're interested, to learn more about the whole thing, to learn more about system internals, which help a lot with performance investigations, to learn more about statistics as well. There's a few books here, a few videos, a few blog posts also. The slides themselves, you can find them here. I'm sure they'll also be posted internally somewhere if you'd like to take a look later. And if we have time for questions, and if you have questions, I'll be delighted to answer if there's anything that you found interesting. And if you want to just talk to me in person about something, I'm going to stay here for a few minutes. I really appreciate that you came. It's late in the evening, and I don't know if I would come to a talk by some random person at 7 in the evening, but I appreciate it, and I hope you enjoyed. Thank you very, very much. Thank you.